Space and time feel simple because they are always present. Every movement happens somewhere. Every thought unfolds within a moment, from the first step taken in childhood to the slow turning of planets overhead. Space feels like a stage, and time feels like a steady current carrying everything forward. They appear separate. One can be crossed, the other can only be waded through. And yet, beneath that familiarity, physics has uncovered something quietly unsettling. At the largest scales of the universe, and at the fastest speeds nature allows, space and time refuse to behave independently. Distances shrink or stretch depending on motion. Moments pass differently depending on gravity. Events that seem simultaneous from one perspective unfold in sequence from another. The rules that govern space alone, or time alone, begin to blur, then dissolve entirely. What once seemed like two fundamental ingredients of reality begin to look more like two expressions of a deeper structure. If you enjoy videos like this, please consider liking and subscribing, and if you feel like it, share where in the world you're listening from tonight. It is always quietly remarkable to see how far these journeys travel. For more than a century, scientists have been carefully testing the nature of space and time using clocks, light, gravity, and motion itself. Experiments conducted on Earth, in orbit, and across the solar system have repeatedly confirmed a surprising result. Space cannot be measured without time. Time cannot be measured without space. Change one, and the other responds. Observatories operated by organizations like NASA and international partners have observed galaxies so distant that their light has been traveling longer than most of cosmic history. That light does not simply reveal where those galaxies are. It reveals when they are. Distance and age arrive together, inseparable, encoded in the same faint signals reaching modern instruments. With telescopes such as the James Webb Space Telescope, astronomers now observe the early universe with unprecedented clarity. These observations do not merely fill in missing details. They quietly reinforce a deeper lesson. Space expands. Time stretches. The universe does not evolve within a fixed stage. The stage itself participates in the story. This realization reshapes more than cosmology. It changes how gravity works, how motion is defined, how cause and effect unfold, even how beginnings and endings are understood. When space and time merge into a single fabric, questions about distance become questions about history. Questions about the future become questions about geometry. Tonight's exploration follows that idea gently and carefully, not as a sudden revelation, but as a gradual shift in perspective. From everyday intuition to physical reality, from separation to unity, from the familiar feeling of passing moments to the deeper structure that quietly binds every event together. If space and time are not separate things, then reality itself may be more interconnected than it appears, not layered, not compartmentalized, but woven. Settle in, let familiar ideas loosen slightly, and allow space and time to begin, slowly, to look like one. Long before equations described the universe, the mind learned to sort reality in practical ways. Some things were far, some things were near, some moments lasted, others passed quickly. Space became the measure of reach, and time became the measure of patience. This division felt natural, almost unavoidable, because it worked. To survive, distance mattered. A predator across an open plain could be seen, judged, and avoided. A shelter too far away meant danger. Space became something that could be scanned, crossed, or escaped. It could be mapped with a body itself, a few steps, a long walk, a mountain that would take days to climb. Time, meanwhile, announced itself differently. It did not stretch beneath the feet or block the path ahead. It arrived as waiting, as hunger returning, as daylight fading. Time could not be outrun, but it could be endured. The cold night would pass, the wound would heal, the seasons would turn again eventually. For an organism trying to stay alive, separating these two ideas made perfect sense. One described where danger was, the other described when relief might come. That intuitive division became deeply rooted. Even language reflects it. Space is described with shapes, distances, and directions. Time is described with flows, arrows, and rhythms. One feels solid, the other feels fleeting. One seems external, the other internal. But intuition, as useful as it is, was never designed to reveal the deeper structure of reality. It was shaped by evolution to solve immediate problems, not cosmic ones. The brain learned to carve the world into categories that helped ancestors survive long enough to reproduce. Accuracy beyond that was unnecessary. This is why certain illusions persist. The ground feels still even as Earth moves through space faster than most aircraft. The sun appears to rise and set even though it is Earth that turns. Perception favours stability and simplicity over precision. It always has. Space and time were treated the same way. They were separated not because they truly were, but because separating them worked well enough. Distance could be estimated by effort. Time could be estimated by memory. No hunter needed to understand that motion through space affected the passage of time. No gatherer needed to consider whether two events were simultaneous from another point of view. Survival did not demand that level of understanding, and so the illusion settled in comfortably. For centuries, even early science followed intuition's lead. Space was treated as a fixed stage. Time was treated as a universal clock ticking the same way everywhere. The universe unfolded within these two separate frameworks, calm and predictable. This picture began to crack only when measurements became precise enough to notice inconsistencies. As instruments improved, nature stopped behaving quite as expected. Light did not cooperate with ordinary ideas of speed. Motion began to interfere with measurement. Time itself appeared to change under certain conditions. These discoveries were not obvious. They emerged slowly through careful experimentation and persistent curiosity. Scientists measuring light in the late 19th century noticed something strange. No matter how fast the observer moved, light always appeared to travel at the same speed. This contradicted common sense. If space and time were truly separate and absolute, speed should simply add together. They did not. At first, this seemed like a technical problem. Then it became a conceptual one. If distance depends on motion and motion depends on time, perhaps space and time are not independent after all. When thinkers like Albert Einstein examined this problem seriously, intuition was no longer treated as an authority. Instead, it became a clue to be questioned. The familiar separation between space and time began to look like a useful approximation rather than a fundamental truth. Einstein did not begin by trying to merge space and time. He began by trying to respect experimental results. The merger followed naturally, almost reluctantly. If light behaves the same for all observers, then measurements of distance and duration must adjust to preserve that fact. Space bends slightly. Time stretches quietly. Neither can remain fixed on its own. From the perspective of everyday life, these effects are tiny. At walking speeds, time behaves as expected. At household distances, space feels rigid and dependable. The illusion remains intact because the universe allows it to. But illusion does not mean false in a careless sense. It means limited. It means locally accurate, globally incomplete. This is where intuition often misleads. It assumes that because something works in one context, it must work in all contexts. Evolution does not care about edge cases. Physics does. The separation of space and time is one such edge case. It works beautifully for daily life. It fails quietly at high speeds, strong gravity, and cosmic distances. Even modern technology must account for this failure. Satellite navigation systems, for example, rely on clocks orbiting Earth. Those clocks tick at slightly different rates than clocks on the ground due to motion and gravity. Without correcting for this difference, positioning errors would grow rapidly. Navigation would drift by kilometers within a single day. NASA routinely incorporate these corrections not as philosophical curiosities, but as engineering necessities. Space and time must be treated together, or systems fail. And yet, despite this evidence, the mind still prefers separation. Space is still imagined as a container, time as a current flowing through it. These metaphors are comfortable. They align with experience. They feel true. Physics suggests something subtler. Space and time may not be things at all in the usual sense. They may be aspects of relationships, ways of describing how events are connected. Remove motion, gravity, and interaction, and their distinction begins to lose meaning. This does not make intuition wrong. It makes it specialized. Just as eyes evolved to see a narrow range of light and ears to hear a limited range of sound, perception evolved to experience space and time in ways that promote survival. Reality, however, is not obligated to conform to those limits. Beneath perception, the universe appears less divided. Distance carries time with it. Duration carries structure. Every event occupies not a place in a moment separately, but a single location in a deeper framework. The illusion of separation persists because it is useful. It organizes experience. It simplifies decision-making. It keeps attention focused where it matters most. But usefulness is not the same as truth. When measurement replaces intuition and precision replaces instinct, reality begins to show a different architecture, one where space and time are not opposing categories, but intertwined expressions of a single underlying structure. The surface remains familiar. The ground still feels solid. Moments still pass. But beneath that familiarity, something quieter and stranger holds everything together. For most of human history, motion seemed simple. Something moved because it was pushed. It stopped because the push ended. Speed added neatly to speed, like footsteps piling up along a road. If a rider threw a stone forward from a moving horse, the stone's speed simply combined the throw with the horse's pace. Nothing mysterious there. This way of thinking worked beautifully at everyday scales. Walk faster and scenery passes more quickly. Ride a cart and the journey shortens. Motion felt like a change layered on top of a stable background. Space stayed put. Time ticked steadily. Objects merely travelled through both. That confidence held for centuries, reinforced by thinkers like Galileo Galilei, who showed that motion looks the same inside a smoothly moving ship as it does on solid ground. Drop a ball below deck and it falls straight down, not diagonally backward. Motion, it seemed, could be ignored unless something accelerated. This insight became part of classical physics. Motion was relative, but time was not. Space could shift perspectives, but time marched on uniformly, everywhere, for everyone. The universe had a single clock and a shared stage. Then speed began to increase. As technology improved, scientists gained the ability to measure motion with greater precision. Trains crossed continents. Telegraph signals raced along wires. Light itself became something to time, not just to see. It was light that first made trouble. Experiments in the 19th century attempted to measure how Earth moved through space by comparing the speed of light in different directions. The expectation was straightforward. If Earth were moving, light travelling along that motion should behave differently from light travelling across it. Distance divided by time should reveal the difference. Simple arithmetic, clean predictions. The results refused to cooperate. No matter how the measurements were arranged, light always arrived at the same speed. Faster instruments did not help. Repeated trials did not help. The universe stubbornly returned the same answer every time. This was not a small discrepancy. It struck at the heart of classical thinking. If speeds simply add together, then motion through space should affect how fast light appears to move. But it did not. That meant something deeper was adjusting instead. Either space was changing or time was, or both. At first, physicists tried to preserve the old picture with small fixes. Perhaps measuring devices subtly contracted. Perhaps timing mechanisms drifted. These ideas worked mathematically, but they felt uneasy. Like patching a leaking ship instead of asking why water was getting inside at all. The deeper problem was this. Speed is distance divided by time. If speed remains constant under all conditions, then distance and time cannot be independent quantities. They must be linked in a way classical intuition had not anticipated. As objects moved faster, strange effects emerged. Lengths appeared shorter along the direction of motion. Durations stretched. Events that seemed simultaneous from one perspective no longer lined up from another. Motion was no longer something layered on top of space and time. It was interfering with them directly. This was deeply unsettling. Common sense insists that time passes the same way regardless of speed. A second feels like a second, whether one is standing still or sprinting. Space seems equally stubborn. A meter looks like a meter no matter how quickly it is crossed. Yet careful experiments contradicted this comfort. Clocks in motion were observed to tick more slowly than clocks at rest, by tiny but measurable amounts. Particles moving near the speed of light survived longer than expected because time stretched for them. These were not philosophical curiosities, they were experimental facts. Organizations such as CERN routinely observe particles accelerated to enormous speeds. Without accounting for changes in time caused by motion, predictions would fail. Detectors would miss events. Data would make no sense. The universe was not misbehaving. Human expectations were. At low speeds, close to everyday experience, these effects fade into invisibility. That is why intuition remained confident for so long. Motion at walking or driving speeds is simply too slow to expose the deeper structure. Space and time appear independent because the universe allows them to masquerade as such. But as speed increases, the disguise slips. The faster something moves, the more space and time refuse to act separately. Distances shrink along the direction of travel. Durations stretch to preserve a deeper consistency. It is as if reality quietly rearranges its measurements to keep certain rules intact, regardless of perspective. One of those rules is that no signal outruns light. Instead of allowing speeds to pile up endlessly, the universe adjusts the measurements themselves. Space flexes, time yields. Motion becomes the lever that reveals the mechanism beneath. This creates a peculiar tension. The faster something goes, the less familiar reality becomes. Motion, once the simplest of ideas, turns into a distorting influence. Not violent or dramatic, but precise and unavoidable. The unsettling part is not that this happens, it is that it must happen. If space and time truly existed as separate, absolute entities, then motion would have no reason to affect them. Speed would be a mere comparison of positions over moments, nothing more. The experiments say otherwise. Even technologies closer to home must respect this. Satellite systems orbiting Earth rely on precise timing to locate positions. Those satellites move quickly and sit higher in Earth's gravitational field. Their clocks tick differently from clocks on the ground. Without correcting for this, navigation errors would accumulate rapidly, drifting by kilometers each day. Groups like NASA do not treat these corrections as optional. They are built into the design. Space and time are adjusted together because motion demands it. At this point, the old picture begins to strain. Space as a rigid grid and time as a universal rhythm can no longer survive unchanged. Motion exposes their dependency. Speed reveals their partnership. And yet, no single statement resolves the tension completely. The pieces suggest a rethinking, but the full shape remains just out of reach. Something deeper is holding the rules together, quietly enforcing consistency across all motion. Space and time resist being pulled apart when speed enters the scene. The universe responds not by breaking, but by redefining what distance and duration mean. Motion, once a simple add-on, becomes the first undeniable crack in the familiar structure. Through it, reality hints that space and time are not separate scaffolds, but adjustable aspects of something unified beneath. The faster things move, the clearer that message becomes, and the universe, patient and precise, seems to insist that the old divisions were never fundamental to begin with. At the turn of the 20th century, physics was not searching for a revolution. It believed it already understood the stage on which nature played. Space was fixed. Time was universal. Motion was something that happened within those boundaries, not something that reshaped them. Into this comfortable picture stepped Albert Einstein, not with a grand plan to rewrite reality, but with a quiet, almost childlike curiosity about light. Light was behaving oddly. For decades, experiments had shown that no matter how fast an observer moved, light always appeared to travel at the same speed. Ride toward a beam or race alongside it, and the result never changed. This was deeply inconvenient. According to classical thinking, speed should stack. If a train moves forward and a lamp on the train shines ahead, the light should move faster relative to the ground. But it did not. This was not a minor puzzle, it was a contradiction. Einstein took the results seriously. Instead of asking how to fix the measurements, he asked what assumptions were being protected too fiercely. The most fragile assumption, it turned out, was not about light at all. It was about time. If the speed of the light is the same for everyone, then something else must give. Either distance changes, or time changes, or both. Einstein followed this thought patiently, without rushing toward conclusions. He imagined simple scenarios. Two observers moving relative to each other. A flash of light sent between mirrors. A clock built from light bouncing back and forth. Nothing exotic, just careful reasoning carried to its end. What emerged was not an adjustment to existing physics, but a shift in perspective. Time, Einstein realized, could not be absolute if light was truly constant. If two observers move differently, they cannot agree on how long events last. Their clocks must disagree. Not because one is broken, but because time itself responds to motion. This idea felt wrong at first. Time had always been treated as the most reliable ingredient of reality. Distance might depend on perspective, but time seemed sacred. Seconds were seconds. Moments marched forward identically for all. Einstein let go of that comfort. In doing so, he introduced what became known as special relativity, though the name arrived later. The principle itself was simple to state, even if its consequences were strange. The laws of physics are the same for all observers moving at constant speed, and the speed of light is the same for all of them. From these two ideas, everything else followed. If two observers move relative to each other, they will disagree about lengths. A fast-moving object appears shorter along the direction of motion. This is not an illusion of sight, but a real difference in measurement. Space adjusts. At the same time, those observers will disagree about durations. A moving clock ticks more slowly compared to one at rest. Again, not because it malfunctions, but because time itself stretches. time adjusts. Crucially, these adjustments are not independent. They are linked. Change the measurement of distance and the measurement of time changes with it. Preserve the speed of light, and both must bend together. Space cannot flex alone. Time cannot stretch in isolation. This was the heart of Einstein's insight. Special relativity did not claim that everything is relative. It claimed something more precise. Certain quantities remain fixed while others adapt. Light speed stays constant. The structure of physical law stays consistent. Space and time, however, become negotiable. This negotiation depends on motion. As relative speed increases, the effects grow stronger. At everyday speeds, they are negligible. A person walking down a street does not age noticeably slower than someone standing still. A car does not visibly shrink as it drives past. The universe is kind enough to hide its complexity when it is not needed. But at extreme speeds, the rules become unmistakable. Particles accelerated in laboratories survive longer than expected because time stretches for them. Muons created in the upper atmosphere reach Earth's surface in greater numbers than classical physics would allow, because their internal clocks run slow relative to the ground. These are not thought experiments. They are measured outcomes. Institutions like CERN rely on these effects daily. Without accounting for changes in time caused by motion, predictions would fail. Experiments would not align with reality. What makes this unsettling is not the math, but the implication. If time depends on motion, then it is not a universal backdrop. If space depends on motion, then it is not a fixed container. Both respond dynamically to how observers move through the universe. Einstein did not set out to unite space and time. He was content to let the equations speak. But the picture that emerged made separation increasingly awkward. Distance and duration appeared less like independent ingredients and more like different projections of something shared. Consider two events. Whether they happen at the same time depends on motion. Whether they happen at the same place depends on time. What one observer treats as simultaneous, another treats as sequential. What one treats as separated in space, another treats as separated in time. There is no universal answer, only consistent ones within each frame of motion. This does not mean reality is subjective. It means reality is structured in a way that does not privilege any single perspective. Space and time adjust so that the deeper rules remain intact. Einstein's contribution was not just a new theory, it was a change in what questions were allowed. Instead of asking how objects move through space over time, physics began asking how measurements themselves depend on motion. The focus shifted from objects to relationships, from absolute quantities to invariant principles. Space and time, once treated as separate bookkeeping tools, began to behave like intertwined aspects of a single framework. Pull on one, and the other responds. Change one, and the combined structure preserves consistency. Einstein himself was cautious with language. He did not rush to poetic conclusions, but others noticed the pattern. If distance and duration transform together, perhaps they are not separate entities at all. Perhaps they are two faces of the same underlying reality. Special relativity did not fully articulate that reality yet. It revealed the strain lines. It showed where intuition failed. It demonstrated that motion forces space and time into cooperation. What had once seemed like independent pillars now behave like coordinated responses to a deeper rule set. A rule set that cares less about how fast one moves, and more about preserving a unified structure beneath all motion. By following a simple question about light, Einstein had quietly changed the question about reality itself. Space and time no longer stood apart, politely minding their own domains. They began to look like different ways of slicing the same fabric. Once motion exposed the weakness in the old picture, physics faced an uncomfortable question. If space and time adjust together to preserve deeper rules, then treating them as separate ingredients may no longer make sense. The universe seemed to be hinting at a different way of organizing reality, one that felt unfamiliar but oddly economical. That reorganization did not arrive all at once. It emerged gradually, as scientists tried to describe what experiments were already showing. The first shift was subtle. Instead of focusing on objects moving through space as time passed, attention began to move toward events. Something happens. A flash of light, a collision, a signal arriving. An event is not just where something occurs or just when it occurs, it is both together. This sounds trivial at first. Of course things happen somewhere and sometime. But classical thinking quietly separated the two. Place could be described without reference to time. Time could be described without reference to place. An event was split into coordinates, then treated as a pair of independent facts. Relativity resisted that separation. If observers moving differently cannot agree on distances or durations, then asking where something happened without asking when it happened becomes incomplete. Likewise, asking when something happened without asking where it happened loses meaning. The two pieces refuse to stand alone. This is where the idea of space-time was born, not as a poetic flourish, but as a practical necessity. Space-time is not a substance. It is not a fabric in the everyday sense. It is a way of describing reality that treats space and time as aspects of a single structure rather than separate arenas. Instead of plotting objects moving through a backdrop, physicists began plotting events within a unified framework. In this framework, an event is the basic unit, not a location by itself, not a moment by itself, but a combination that cannot be pulled apart without losing information. This shift takes some getting used to because it runs counter to habit. Imagine trying to describe a meeting without mentioning when it occurred, or trying to describe a memory without any sense of where it took place. In daily life, these omissions feel unnatural. Relativity formalized that intuition. It made it explicit. Space and time were no longer independent descriptors. They became coordinates of the same thing. The language of dimensions emerged as a way to talk about this structure, though the word itself can be misleading. In everyday use, a dimension sounds like an extra direction, something added on. In physics, a dimension is simply a way to specify an event fully. Space has dimensions because one needs several pieces of information to say where something is. Time adds another piece, not as an afterthought, but as an equal partner. Together, they locate events completely. Importantly, this does not mean time becomes space or space becomes time. They remain distinct in character. One still feels directional, the other still feels expansive, but they are woven into a single description. The mathematician who helped clarify this picture most clearly was Hermann Minkowski. In the early 20th century, he showed that Einstein's ideas could be expressed elegantly by treating space and time as parts of a single geometric structure. His formulation did not add new physics, it revealed what had already been implied. Minkowski famously remarked that space by itself and time by itself were doomed to fade away, leaving only a union of the two. This was not philosophy, it was bookkeeping. The equations worked better, the descriptions became simpler, the contradictions dissolved. Within space-time, motion takes on a new meaning. Objects do not merely move through space as time ticks by. They trace paths through space-time. Every object, whether moving quickly or standing still, progresses through this combined structure. Stillness becomes a special case of motion, not an absence of it. This reframing resolves earlier puzzles without drama. Why do different observers disagree about simultaneity? Because simultaneity is not absolute. It depends on how space-time is sliced into space and time by each observer. Why do lengths and durations change with speed? because observers are measuring different projections of the same underlying structure. Nothing magical is happening. Nothing is breaking. The universe is simply being described in a way that matches how it behaves. What makes this adjustment difficult is not the science, but the intuition. The mind insists on separating what experience presents as separate. Space feels like a container. Time feels like a flow. Space-time feels abstract because it is not directly sensed. And yet it quietly governs everything. Consider a simple action like sending a message. The act has a location and a duration. It cannot be placed anywhere without also being placed at a time. Remove either piece, and the description collapses. In space-time terms, the message is an event with a definite position in the combined structure. This perspective becomes unavoidable when dealing with cosmic scales. Light from distant galaxies carries not just information about where those galaxies are, but when they were. Distance becomes a measure of time elapsed. Looking far away means looking far back. Space and time arrive together in the same signal. NASA regularly interpret observations this way. Astronomers do not treat distance and age as separate quantities. They are linked. A galaxy billions of light years away is also billions of years in the past. The measurement does both jobs at once. Space-time also simplifies gravity, though that story unfolds later. For now, what matters is the conceptual shift. Events replace objects as the primary focus. Relationships replace absolute positions. Measurements become contextual but not arbitrary. This does not make reality vague. It makes it precise in a different way. In space-time, nothing exists purely in space, frozen in time. Nothing exists purely in time, detached from location. Every occurrence is a blend. Every fact is situated. Every change traces a path through the combined structure. The familiar separation survives only as a convenience, useful at low speeds and small scales. Beneath it lies a quieter organization, one that does not divide reality into where and when, but holds them together as inseparable aspects of what happens. The universe does not ask space and time to cooperate. It assumes they already do. And in that assumption, the old categories begin to dissolve, replaced by a deeper unity where events are the true currency of reality, and where nothing exists in only one half of the story. When Einstein first described how motion reshapes measurements of distance and duration, the implications were clear, but the picture was still fuzzy. Space and time adjusted together, yes, but how exactly were they connected? What held them in alignment? What ensured that every observer, no matter how they moved, still described the same underlying reality? The answer came not from new experiments but from geometry. Hermann Minkowski had been one of Einstein's teachers years earlier. Where Einstein approached problems physically, Minkowski approached them spatially. He asked how these strange results could be seen, not just calculated. What shape did reality have to take for these rules to hold so stubbornly? The solution was surprisingly elegant. Instead of imagining space as a container and time as something flowing through it, Minkowski treated them as parts of a single geometric structure. Not a place things sit inside, but a framework that defines how events relate to one another. In this view, space-time is not the stage, it is the script. Geometry had long been used to describe space. Lines, distances, angles. Minkowski extended this idea to include time, not as an add-on, but as an essential direction within the same structure. Events could be plotted not on separate maps of where and when, but within one unified layout. This did not make space-time physical in the everyday sense. It did not turn it into a substance or a fabric you could touch. Instead, it gave space-time shape. And shape changes everything. In everyday life, straight lines feel simple. Walk forward without turning, and the path feels straight. Throw a ball and it follows a smooth arc. Geometry seems intuitive, almost obvious. But that intuition comes from living at low speeds and weak gravity. In spacetime, the idea of straightness takes on a deeper meaning. A straight path in spacetime is not defined by visual appearance. It is defined by consistency. It is the path that requires no force to follow, no steering, no pushing, just motion unfolding naturally according to the structure itself. This is why straight paths can look curved when projected into ordinary space. Consider an airplane flying a long-distance route across Earth. On a flat map, the path curves dramatically. It looks inefficient, even strange. But on the curved surface of the planet, that same route is the straightest possible path. The geometry of the surface determines what straight means. Minkowski showed that spacetime works the same way. An object moving freely through spacetime follows the straightest possible path allowed by that geometry. To an observer focused only on space, the motion may look curved or accelerated. To spacetime itself, nothing unusual is happening. The object is simply following the shape laid out beneath it. This reframing removes mystery without removing wonder. Instead of asking why objects move the way they do, the question becomes what shape spacetime has. Motion is no longer something imposed on the universe. It is something permitted by its structure. In Minkowski's formulation, space and time are not passive backgrounds. They are active participants in defining what motion looks like. Distances and durations adjust automatically because geometry demands it. This also explains why different observers measure different lengths and times without contradiction. They are slicing the same geometric structure in different ways. One observer's definition of space tilts slightly into another observer's definition of time. The underlying space-time remains the same. Nothing changes physically, only the perspective changes. This idea is deeply calming once it settles in. The universe is not chaotic. It is consistent. Every observer carries their own coordinate system, but all coordinate systems fit within the same geometric whole. Minkowski's spacetime replaced a patchwork of rules with a single principle. Preserve the geometry and everything else follows. Even light fits naturally into this picture. Light does not slow down or speed up because spacetime geometry constrains how paths can be traced. Light follows special routes that sit at the boundary between what can influence what. These paths define the structure itself. Physicists often describe spacetime as having an unusual geometry compared to everyday space. Distances behave differently. Time contributes with a different character, but no equations are required to appreciate the result. Geometry is doing the bookkeeping quietly in the background. Once this perspective is adopted, earlier puzzles soften. Why does motion affect time? Because time is part of the geometry being navigated. Why does distance shrink at high speeds? Because different observers carve the same structure into space and time differently. Why do straight motions appear curved under certain conditions? Because straightness depends on the shape of the underlying framework. This geometric view proved powerful far beyond its original purpose. It laid the groundwork for understanding gravity not as a force, but as a feature of spacetime itself. But even without that extension, Minkowski's insight completed Einstein's early work. Spacetime stopped being a philosophical suggestion and became a precise tool. Modern science uses this language constantly, often without drawing attention to it. When astronomers calculate trajectories, when engineers synchronize clocks on satellites, when particle physicists analyze collisions, they're working within Minkowski's framework. Geometry ensures that results remain consistent across motion and perspective. Institutions such as CERN rely on this structure implicitly. Particles accelerated to enormous speeds follow paths that only make sense when spacetime geometry is respected. Without it, predictions would drift, measurements would conflict, and experiments would lose coherence. What makes this remarkable is how quietly it all works. There is no dramatic signal announcing spacetime's shape, no sensory cue revealing geometry at work. It simply governs relationships, ensuring that cause and effect remain intact, that signals propagate reliably, and that observers can disagree without contradiction. Spacetime, in this view, is not something objects sit inside. It is the network of relationships that tells objects how to move, how to age, and how to interact. It is structure, not container. Once geometry enters the story, reality feels less like a collection of things and more like a pattern that remains stable even as perspectives shift. Straight lines become a matter of context. Curves become a matter of projection. Motion becomes a conversation between objects and the shape beneath them. Minkowski did not change the universe. He changed how it was read. By revealing the geometric nature of spacetime, he showed that space and time were never meant to be separate pages in a ledger. They were lines in the same sentence, shaped by the same grammar. And like any good grammar, spacetime's rules operate quietly. They do not draw attention to themselves. They simply ensure that the universe makes sense from every point of view at every speed. Geometry, it turns out, is not just a tool for measuring reality. It is the language reality uses to speak. Time feels like it moves because everything experienced moves within it. Morning becomes afternoon. Shadows shift. Clocks advance with quiet persistence. Even without looking, the sense of forward motion is unmistakable. Something is always arriving, and something else is always slipping away. From experience alone, it feels obvious that time flows. Physics, however, tells a calmer and stranger story. In the physical description of the universe, time does not rush forward, hesitate, or slow down on its own. It does not surge like a river or tick like a machine. Instead, it sits alongside space as part of the structure that events occupy. Not something that happens, but something that is. This difference between experience and description is subtle, and it takes a moment to settle. In everyday life, time is felt through change. Hunger returns, light fades, muscles tire, memory accumulates. None of this feels static. It feels directional. Time appears to carry everything with it. But physics separates the sensation of change from the framework used to describe it. In spacetime, time is treated as a dimension, not a direction of motion, but a way to locate events. Just as space provides multiple ways to specify where something happens, time provides a way to specify when it happens. Together, they define an event completely. Nothing in that description requires time itself to move. To see why this matters, consider how motion works in space. A road does not move past a traveller. The traveller moves along the road. The road provides structure, not motion. In physics, time plays a similar role. It provides structure for change, but it does not cause change by flowing. This is deeply unintuitive. The brain strongly prefers the image of time as a current, sweeping everything forward. That metaphor feels natural because consciousness experiences only one direction. Memories accumulate. Anticipation points ahead. There is no recall of the future, only the past. Physics does not deny this experience. It simply describes it differently. In spacetime, every event exists at a particular position in both space and time. From that perspective, change is a sequence of events arranged along a path. Motion through time is not something imposed by time itself. It is something objects do by existing and interacting. Every object traces a path through space-time. That path always advances in time, just as it may wander through space. The progression comes from the object's existence, not from time pushing it along. This distinction becomes clearer in extreme conditions. At very high speeds, clocks tick more slowly compared to those at rest. This effect has been measured countless times. Particles moving near the speed of light survive longer than expected. Atomic clocks flown on aircraft return slightly out of sync with those left on the ground. Satellites must correct for these differences continuously to function properly. NASA account for these effects as part of routine engineering. Without doing so, navigation systems would drift by kilometers within a single day. These corrections are not optional. They're built into the operation of modern technology. What matters here is how these effects are explained. Time does not slow down because it encounters resistance or thickens at high speed. It slows because motion through space-time changes how durations are measured. The structure remains. The path through it changes. This is why physics resists describing time as a flow. Flow implies motion relative to something else. It implies a direction independent of objects. In space-time, there is no external frame relative to which time could flow. There is only the structure itself and the paths traced within it. This perspective also explains why there is no universal present. Two observers moving differently will disagree about which distant events are happening now. This is not a failure of synchronization. It is a feature of space-time. The notion of a single global moment does not exist in the physical description. Again, this feels wrong only because experience suggests otherwise. Daily life operates within such narrow ranges of speed and gravity that differences vanish. The illusion of a shared present holds perfectly well where survival happens. But as with space and time being separate, usefulness is not the same as fundamentality. The idea that time does not flow does not mean nothing happens. It means that happening is not driven by time itself. Events do not unfold because time pushes them forward. They unfold because physical processes occur in sequence along paths through space-time. Change comes from interaction, from cause and effect, from energy rearranging itself. Time simply orders those changes. This ordering is precise and dependable. It allows clocks to be built. It allows predictions to be made. It allows history to be reconstructed and futures to be anticipated. None of this requires time to move. It requires only that time exists as a dimension within which events are arranged. This way of thinking becomes especially clear in physics equations. While the details are not needed here, the structure matters. Equations describe how systems change relative to time. Time appears as a coordinate, not as an agent. It labels progression. It does not create it. Even when change is described mathematically, time does not act. It is referenced. This is why physicists are comfortable treating time as something that can stretch, compress, and vary with conditions. These variations affect measurement, not existence. Time remains part of the structure. It does not speed up or slow down in any absolute sense. The discomfort usually comes from language. Words like flow, passage, and arrow are metaphors layered onto experience. They're useful for storytelling and memory, but they do not reflect how physics organizes reality. Physics prefers quieter terms: coordinate, dimension, interval. These words sound dry, but they are surprisingly gentle. They describe a universe that does not rush, a reality that does not push itself forward, a structure that simply exists, allowing events to be arranged without urgency. Only near the end does philosophy begin to peek through. If time does not flow, then the sensation of flow must arise elsewhere, from consciousness, from memory, from how brains record change rather than from how the universe moves. That question belongs later. For now, what matters is the physical description. Time, in space-time, is not a river carrying everything along. It is a direction within a structure. Objects move, processes unfold, events occur. Time itself remains still, and that stillness is not empty or cold, It is precise, reliable, calm. Rather than diminishing reality, this view opens it. It suggests that change does not need to be driven by an invisible current. It emerges naturally from relationships, motion, and interaction. Time does not rush forward, it simply allows everything else to happen. And once that idea settles, curiosity begins to replace unease. For centuries, gravity was treated as the most familiar of forces. Drop a stone, and it falls. Throw it upward and it slows, stops, then returns. Planets circle the sun as if held by invisible strings. The explanation felt intuitive. Massive objects pull on one another. The bigger the mass, the stronger the pull. Distance weakens the effect. Simple, reliable, and deeply convincing. This picture worked extraordinarily well. It allowed astronomers to predict eclipses, chart planetary orbits, and send spacecraft across the solar system with remarkable accuracy. Gravity, as a force, seemed settled. And yet, beneath that success, something quietly refused to fit. According to the earlier ideas about space and time, forces act within space and unfold over time. A force pulls an object from here to there, now to later. But as space and time themselves began to lose their absolute status, gravity started to look suspiciously out of place. If space and time adjust with motion, how could gravity operate independently of them? The question bothered Albert Einstein for years. He was not dissatisfied with the predictions of classical gravity. He was uneasy about its meaning. Gravity appeared to act instantly across distance, as if space itself carried messages faster than light. That alone was enough to raise concern. Einstein began with a simple observation. Falling feels like weightlessness. An object dropped in a closed elevator experiences no gravity internally. Everything falls together. From the inside, gravity seems to vanish. Conversely, standing still on the ground feels like being pushed upward, not pulled downward. The ground presses back, holding the body in place. This reversal was subtle but profound. Perhaps gravity was not a force acting on objects at all. Perhaps it was something about the stage on which motion takes place. Einstein followed this idea patiently, and after years of work it led to general relativity. The core idea is surprisingly gentle. Massive objects do not pull on other objects. Instead, they shape space-time. They alter its geometry. Motion then follows that shape naturally. In this view, space-time is not flat and rigid. It is flexible. Mass tells space-time how to curve. Space-time tells objects how to move. The familiar sensation of gravity emerges from this relationship. Imagine space-time as a structured landscape rather than an empty container. Place mass into that structure, and the geometry changes. Paths that were once straight now bend. Objects moving freely follow these curved paths, not because they are being pulled, but because straight motion in a curved geometry looks like acceleration. This is why gravity feels unavoidable. An object in free fall is not being dragged downward. It is moving straight through space-time. The sensation of weight appears only when that motion is interrupted, when the ground prevents the object from following its natural path. This reframing removes a long-standing mystery. Why do all objects fall at the same rate regardless of their mass? In the geometric view, they're all following the same space-time structure. Their internal properties do not matter. The path is set by geometry, not by force. The predictions of this idea were bold and testable. Light, for example, should be affected by gravity even though it has no mass. If space-time is curved near massive objects, light should follow that curvature. During a solar eclipse in 1919, starlight passing near the Sun was observed to bend by exactly the amount general relativity predicted. The result was dramatic and precise. Time, too, should be affected. Clocks near massive objects should tick more slowly than clocks farther away. This effect has been confirmed repeatedly. Atomic clocks placed at different heights above Earth fall out of sync by measurable amounts. Satellites must correct for this difference continuously. NASA incorporates these corrections as part of standard operation. Without them, positioning systems would drift rapidly. What once sounded abstract becomes practical engineering. What matters here is the interpretation. Gravity does not slow clocks by acting on their internal mechanisms. It alters the structure of space-time in which those clocks exist. Time itself is shaped by mass. This is why gravity cannot be described as acting only in space. It reshapes time as well. The deeper the gravitational influence, the more space-time is altered, both spatially and temporally. This also explains why gravity and acceleration are so difficult to distinguish locally. Being pressed into a seat by a rocket feels identical to standing on a planet. In both cases, space-time paths are being redirected. The experience arises from geometry, not force. The elegance of this picture lies in its economy. There is no need for invisible strings or instantaneous pulls. There is only structure and motion. Objects move as straight as they can. Space-time provides the shape of straightness. Even planetary orbits become easier to understand this way. A planet is not being tugged endlessly toward the sun while trying to escape. It is following a curved path through space-time shaped by the sun's mass. The orbit is not a compromise between falling and missing. It is the natural geometry of the system. This geometric view also explains why gravity affects everything equally. Energy, mass, light, even pressure contribute to shaping space-time. Nothing is exempt. Everything participates. It also reveals why gravity is so difficult to unify with other forces. Gravity is not something happening within space-time. It is space-time behaving. Once this perspective is accepted, earlier ideas fall into place. Space is no longer a passive arena. Time is no longer an independent clock. Both respond together to mass and energy. They bend as a single entity. They cannot be reshaped separately. This unity is not decorative. It is necessary. If space curved without time changing, motion would become inconsistent. If time slowed without space adjusting, cause and effect would fracture. The universe preserves coherence by bending both together, always. General relativity does not replace earlier physics at everyday scales. It quietly reduces to familiar rules when gravity is weak and motion is slow. The old picture survives where it works. But beneath it lies a deeper description, one that treats gravity not as a force acting across distance, but as geometry expressing itself through motion. Objects do not fall because they are pulled. They fall because space-time tells them that this is the straightest path available, and in that instruction lies a final reinforcing lesson. Space and time are not separate ingredients responding independently. They form a single structure. They bend together, guide together, and define motion together. There is no gravity of space alone, no gravity of time alone. There is only space-time quietly shaping everything that moves within it. By the time gravity was understood as geometry rather than force, the idea was elegant. But elegance alone is not enough in science. Reality has a habit of disagreeing politely, and only careful observation can decide whether a theory belongs to the universe or merely to the imagination. In the case of space-time, the universe answered clearly. One of the earliest confirmations arrived not from falling objects or planetary motion, but from light itself. According to the geometric picture, light does not travel through space as if space were empty and indifferent. Light follows the structure of space-time. If space-time is curved near massive objects, then light's path should curve as well. This was a bold claim. Light had long been treated as massless and untouchable by gravity. If gravity were truly a force pulling on mass, light should pass straight through, unaffected. But if gravity were geometry, Light would have no choice but to follow the curved paths laid out beneath it. The test came during a solar eclipse in 1919. As the moon briefly blocked the sun, stars near its edge became visible. Their apparent positions were measured carefully and compared to where they should have appeared if space were flat. They were shifted. The starlight had bent slightly as it passed near the sun, exactly as general relativity predicted. The effect was small but unmistakable. Geometry had left a visible signature on the sky. Since then, light bending has been observed repeatedly and with increasing precision. Entire galaxies act as lenses, warping and magnifying the light of objects behind them. Rings, arcs, and distorted shapes appear not because light misbehaves, but because space-time curves on cosmic scales. Astronomers now use this effect routinely. It allows them to map invisible mass, including dark matter, by observing how space-time bends light around it. What began as a theoretical prediction has become a practical tool. Time, too, revealed its flexibility. General relativity predicted that time should run at different rates depending on gravity. Clocks closer to massive objects should tick more slowly than clocks farther away. This was not a metaphor. It was a measurable difference. At first, the effect seemed too small to notice, but as clocks became more precise, the difference emerged clearly. Atomic clocks placed at different heights above Earth drift out of sync exactly as predicted. A clock on a mountain runs slightly faster than a clock at sea level. The difference is tiny, but real. Satellites orbiting Earth experience both weaker gravity and higher speeds. Both effects alter time. Their onboard clocks tick at rates different from those on the ground. Without correction, navigation systems would quickly become unreliable. NASA accounts for these differences continuously. Positioning systems depend on timing accuracy, measured in billionths of a second. Ignoring space-time effects would cause errors to grow by kilometers each day. What once sounded abstract now quietly keeps everyday technology working. Motion adds another layer of confirmation. Clocks in motion tick more slowly than clocks at rest. This has been tested with aircraft carrying atomic clocks, with particles racing through accelerators, and with satellites circling Earth. Every experiment agrees. Time adjusts with motion. In particle laboratories, unstable particles moving near the speed of light survive longer than expected when measured from the laboratory frame. Their internal processes slow down relative to observers at rest. This is not interpretation. It is counted in detectors and recorded in data. Facilities like CERN rely on these effects as part of routine operation. Predictions would fail without them. Entire experimental programs depend on space-time behaving exactly as described. Even Earth itself confirms the picture. The planet's rotation and gravitational field influence how time passes across its surface. Extremely precise clocks can detect differences between continents, elevations, and even subtle changes caused by tides. Time is not uniform across Earth. It varies with position and motion, just as space-time predicts. These confirmations share a quiet quality. There is no single dramatic moment where space-time announces itself. Instead, it appears wherever measurement becomes careful enough. In light paths, in clock rates, in particle lifetimes, in satellite systems. The consistency is the key. Each effect could be dismissed individually as an anomaly or technical detail. Taken together, they form a pattern too coherent to ignore. Space and time behave as parts of a single structure. They stretch, bend, and adjust together under mass and motion. This is not interpretation layered on top of data. It is the simplest description that fits all observations at once. Importantly, none of this requires belief. It requires calibration. Engineers, astronomers, and physicists do not debate whether space-time exists when designing systems. They use it. The theory earns its place by working, repeatedly, quietly, reliably. The universe seems remarkably cooperative in this regard. It does not hide space-time's influence behind rare phenomena. It writes it everywhere, from the bending of distant galaxies to the timing signals guiding phones and vehicles on Earth. What changes with familiarity is not the evidence, but the sense of strangeness. At first, curved space-time sounds exotic. Over time, it becomes routine. Light bends, clocks drift, orbits precess, predictions match measurements. The unusual becomes ordinary. This is often how reality reveals itself, not with spectacle, but with consistency. Space-time is not an abstract idea floating above observation. It is a framework tested against nature and found to fit. Again and again, across scales vast and small, the sky itself carries the record, in bent starlight, in delayed signals, in warped images of galaxies billions of light-years away. These are not artistic distortions, they are measurements of structure. When the universe is read carefully, it does not describe space and time as separate stages. It presents them as a unified geometry, one that shapes motion, guides light, and governs the passage of events. What once seemed like an intellectual convenience reveals itself as a physical reality. Space-time is not a metaphor, it is written into the sky. From the inside, space-time does not feel dramatic. There is no sensation of bending or stretching beneath the feet, no awareness of geometry guiding each step. Life unfolds at a human pace, where mornings arrive, bodies tire, and rest restores what motion spends. Everything feels still enough to ignore the deeper structure entirely. And yet, every moment of living is a journey through space-time. Aging is the most familiar example. Cells divide, proteins fold, memories accumulate. None of this happens outside time. Each biological process traces a path forward through duration. From a space-time perspective, aging is not something that happens to time. It is something bodies do within it. A steady progression along a personal route through the universe. Resting, too, is motion of a different kind. Lying still does not pause time or halt movement. The body continues to age, breathe, and repair. The planet rotates. Earth orbits the sun. The solar system drifts through the galaxy. Even at rest, nothing stops. Stillness, it turns out, is a local illusion. From everyday experience, standing still feels like the absence of motion. Feet are planted. Surroundings appear fixed. But physics paints a busier picture. Earth rotates once roughly every 24 hours. At the equator, that motion carries everything eastward at more than 1,000 kilometers per hour. Earth also orbits the Sun at about 100,000 kilometers per hour. The Sun itself moves through the Milky Way even faster. All of this happens quietly, without sensation. The reason is simple. Motion only feels like motion when it changes. Smooth, steady movement fades into the background. This is why riding in an airplane at cruising altitude feels calm, while turbulence demands attention. The body notices acceleration, not constant speed. Space-time treats all motion the same way. There is no preferred state of rest. Standing still on Earth is simply moving along with Earth's space-time path. From another perspective, it is a complicated curve through space and time combined. Walking adds another layer. A person walking across a room changes position in space while continuing to move forward in time. From a space-time point of view, the path tilts slightly. More motion through space means slightly less motion through time, though the effect is far too small to notice at human speeds. This trade-off becomes important only when speeds approach the limits allowed by nature. At everyday velocities, time behaves as expected. A walk does not noticeably slow aging. The universe is forgiving at human scales, but the principle remains. Motion through space and motion through time are linked. Everyone is always moving through space-time at a combined pace. How that motion is divided depends on speed, gravity, and circumstance. Even standing quietly involves constant progression through time. The path does not pause. It simply follows the straightest route allowed by the surrounding space-time. This perspective reframes familiar experiences gently. Sleep, for example, feels like a gap. Hours pass unnoticed. Conscious awareness switches off, then resumes. From the outside, however, nothing stops. The sleeper continues along their space-time path. Processes continue. Clocks advance. The difference lies only in perception. Waiting works the same way. Time feels slow when attention is fixed on it. It feels fast when attention is elsewhere. Physics does not adjust for impatience or boredom. The structure remains the same. Only experience changes. This contrast highlights an important distinction. Human time is psychological. Physical time is structural. Psychological time stretches and compresses based on emotion, attention, and memory. Physical time orders events regardless of how they are felt. Space-time concerns itself with the latter, not the former. The separation explains why time can feel inconsistent without being inconsistent. Experiments with precise clocks show no sympathy for human experience. Atomic clocks tick steadily, whether they are watched or ignored. They respond to motion and gravity, not mood. Their behavior matches space-time predictions exactly. NASA relies on this reliability constantly. Space missions depend on precise timing to navigate vast distances. Signals travelling between Earth and spacecraft must be accounted for carefully. Delays caused by distance and motion are not inconveniences. They are features of space-time that engineers work with daily. Even the act of measuring time reveals constant motion. A clock does not measure time flowing past it. It counts repetitive processes occurring within it. Vibrations of atoms, oscillations of electromagnetic fields. Each tick marks an event, a location in space-time. The sequence of ticks traces a paille. From this view, a lifetime is not something time does to a person. It is the path a person traces through space-time from birth onward. This idea may sound abstract, but it quietly simplifies many things. There is no need to imagine time pushing people forward or dragging them along. There is no universal conveyor belt carrying everything toward the future. There are only paths, each one shaped by circumstances, motion, and gravity. Some paths are steeper through time and slower through space. Others tilt differently, but all are valid. All exist within the same structure. Even the idea of being present changes subtly. The present moment feels sharp and immediate, but physically it is simply the current location along a personal space-time path. There is no cosmic spotlight marking now across the universe. Each observer carries their own present with them, defined locally. This does not make reality fragmented. It makes it intimate. Space-time does not demand a shared stillness. It accommodates constant motion effortlessly. It allows planets to orbit, cells to divide, clocks to tick, and people to pause for breath without ever stopping the deeper progression. Underneath quiet moments, motion continues, not hurried, not forced, just steady and precise. Every heartbeat, every breath, every step taken or not taken is part of a continuous journey. Not through space alone, not through time alone, but through both together. Living inside space-time means never truly standing still, and yet it also means that stillness can feel peaceful, because motion does not need to announce itself to be real. It simply carries on, calmly, beneath everything. Once space and time are understood as deeply connected, a curious question begins to surface. If they form a single structure, can one exist without the other? Could there be space with no time passing through it? A universe frozen, extended, but utterly still. At first glance, the idea seems simple. Space feels tangible. It can be pictured as a vast expanse, even if nothing happens within it. Time, by contrast, feels like the ingredient that brings change. Remove time and perhaps space could remain, like an empty stage after the play has ended. Physics approaches this idea more cautiously. In the physical description of the universe, space is not defined independently of events. It is defined by relationships. Distances matter only because something can be here rather than there. Positions matter because something occupies them, even if that something is only a field or a particle. Without events, space becomes strangely difficult to specify. This becomes clear when physicists attempt to describe a frozen universe. Imagine a cosmos where nothing changes. No motion, no interaction, no processes unfolding. Every object, if objects can still be said to exist, remains exactly as it is. From the inside, nothing would be observable. No clocks could tick because ticking requires change. No measurements could be made because measurement is itself an event. Without time, observation collapses. This does not mean such a universe is logically impossible. It means it resists physical description. In physics, space is not an abstract grid floating independently of activity. It is defined through interactions and relationships that unfold over time. Remove time, and the very tools used to describe space lose their meaning. This is why frozen universes tend to exist more comfortably in mathematics than in physics. Mathematically, it is possible to write down static structures, geometries that do not evolve, shapes that simply are. These descriptions are internally consistent. They do not contradict themselves. But physics demands more than consistency. It demands connection to observation. A universe with space but no time would offer no observations. No signals could travel. No light could propagate. No distances could be compared. Because comparison requires a sequence of events. Even the act of defining a location requires some process that distinguishes it. Physics resists descriptions that cannot, even in principle, be tested. This resistance shows up clearly in cosmology. When scientists describe the large-scale structure of the universe, they do not speak of space alone. They describe space-time evolving. Expansion, curvature, and structure formation are all changes. They rely on time as much as on distance. Attempts to remove time entirely tend to turn dynamic questions into static puzzles that no longer resemble the universe we observe. Even so, physicists have explored the idea carefully. Some approaches ask whether time could emerge from a more fundamental description, while space exists at a deeper level. Others reverse the question, asking whether space might emerge from more basic relationships, with time playing a different role. In these discussions, time often proves harder to eliminate than expected. Space without time struggles to accommodate causality. Cause and effect rely on order, one event leading to another. Without time, there is no before or after. Physics relies heavily on this ordering. Laws describe how systems evolve. Predictions depend on sequences. A static universe allows no evolution. Laws lose their purpose. Prediction becomes meaningless because nothing can change. This does not make the idea useless. It makes it limited. Frozen descriptions can be helpful as approximations. Physicists sometimes describe systems as static to simplify calculations. A star may be treated as unchanging over short intervals. Space near Earth may be treated as fixed for everyday engineering. These approximations work because time is still present, just temporarily ignored. Remove time completely, and the approximation breaks. There's also the question of information. Information is not a static thing. It is encoded, transmitted, and transformed. All of these processes require time. A universe with space but no time would be unable to store or communicate information. Without information, distinctions fade. Structure becomes meaningless. This is one reason physics tends to treat spacetime as the fundamental arena, not space alone. Even in theories that explore exotic possibilities, time remains stubbornly present. It may behave strangely. It may emerge from deeper principles. It may even break down under extreme conditions, but it rarely disappears entirely. That said, physics does not close the door completely. At very small scales, near the limits of current understanding, some theories suggest that the familiar notion of time may dissolve. In these regimes, space and time may both give way to something more abstract. Whether that something resembles space without time is still unclear. What physics resists most strongly is not the absence of time, but the absence of consistency. Any proposal must still allow for cause and effect, for measurable relationships, for a way to connect theory with observation. Space alone struggles to meet these demands. This is why most physical descriptions return, again and again, to events rather than structures. Something happens. That happening defines both where and when. Remove either aspect, and the description becomes incomplete. The idea of space existing without time remains intriguing precisely because it highlights how much of reality depends on change. It invites imagination without granting certainty. Perhaps space could exist as a static geometry, timeless and unchanging. Perhaps such a structure could exist without observers, without processes, without history. Or perhaps space, like distance and position, only gains meaning through temporal relationships. Physics for now leans toward the latter, but it does so gently. There is no final declaration here, no definitive ruling, only a careful boundary drawn between what can be described, what can be measured, and what remains speculative. The question remains open, not because it lacks importance, but because it reaches beyond current evidence. Can space exist without time? Physics does not say no. It simply says that if it can, it would be very different from anything that has ever been observed, and that uncertainty held calmly leaves room for curiosity to continue its quiet work. If space without time feels strange, the mirror question feels even stranger. Can time exist without space? Can moments pass if there is nowhere for them to unfold? Can duration survive without distance, structure, or location? At first glance, time alone feels easier to imagine. After all, time is often treated as something abstract. It is counted, remembered, anticipated. It seems less tied to physical form than space. One might picture time flowing even if nothing occupies it, like an empty schedule waiting to be filled. Physics approaches this idea with careful hesitation. In physical descriptions, time is not a freestanding substance. It does not exist independently as a ticking background. It gains meaning through change, and change requires something to change. Without space, there are no positions to shift between, no configurations to rearrange, no relationships to evolve. Time without space begins to lose its anchor. This becomes clearer when considering what time actually measures. A clock does not detect time itself. It tracks repeated physical processes. Vibrations, oscillations, transitions between states. Each tick marks an event. Remove space, and those processes lose their setting. Even the simplest clock requires structure. Something must exist in one state, then another. Those states must be distinguishable. Distinction requires separation. Separation requires space, even if that space is microscopic or abstract. Without space, sequence collapses. Physics relies heavily on order. One event follows another. Cause precedes effect. Signals propagate. All of this assumes a framework where events can be located relative to one another. Time provides order, but space provides context. Remove context and order becomes meaningless. This is why time alone struggles to stand as a physical concept. It can be labelled, but not operationalized. It can be imagined, but not measured. Cosmology brings this issue into sharper focus. When scientists describe the history of the universe, they do not speak of time unfolding in isolation. They describe space-time evolving together. Expansion is not something that happens in time to space. It is something space-time does as a whole. Measurements of the universe's early stages rely on this partnership. Observations of distant galaxies reveal not only how far away they are, but how far back in time they appear. Distance and age arrive together in the same signal. NASA routinely interprets these observations through space-time models. When telescopes detect ancient light, they are not simply looking far away. They are looking deep into cosmic history. Space and time are inseparable in the data. This inseparability becomes especially important near the beginning. As scientists trace the universe backward, space contracts, distances shrink, densities rise, temperatures increase. Time does not tick alone. It is bound to the changing structure of space itself. Approaching the earliest moments, familiar descriptions begin to strain. The idea of time flowing through a fixed background stops making sense because there is no fixed background. Space itself is evolving rapidly. The framework that gives time meaning is changing. In these extreme conditions, the notion of time existing independently becomes hard to support. Some theoretical approaches explore whether time might emerge from deeper relationships, perhaps arising from quantum processes or informational structures. In these views, time is not fundamental, but a derived concept that appears only when systems interact in certain ways. What these approaches share is an acknowledgement that time requires structure. Whether that structure is spatial, relational, or informational, time does not stand alone. Even attempts to define time purely mathematically tend to rely on parameters that represent change within a system. Without a system, the parameter has nothing to describe. This does not mean time is unreal. It means it is contextual. Human experience often blurs this distinction. Time feels personal. It speeds up during joy, slows during boredom. These variations are psychological, not physical. They reflect how attention and memory work, not how space-time behaves. Physics remains indifferent to this experience. It treats time as an ordering tool, not a sensation. That ordering only becomes meaningful when events can be distinguished, compared, and related. Without space, events cannot be separated. Without separation, sequence collapses. Without sequence, time loses its role. There is also the issue of causality. Cause and effect require not just order, but influence. Something must affect something else. Influence travels. It propagates. Even at the speed of light, it requires a medium of relationships. That medium is space-time. A universe with time but no space would have no way for causes to produce effects. Everything would happen everywhere and nowhere at once. Physics does not support such a description. That said, physics does not close the discussion entirely. At the deepest levels of current theory, near the limits of quantum gravity, the familiar concepts of space and time may dissolve together. Some models suggest that neither space nor time is fundamental, but that both emerge from more basic ingredients. In these models, asking whether time can exist without space may be like asking whether temperature can exist without particles. The question assumes a separation that may not apply. Still, within all tested physical descriptions, time without space remains elusive. Whenever time appears, space or structure appears with it. Whenever space disappears, time becomes undefined. The two rise and fall together, at least within the universe that has been observed. This parallel with the earlier question is not accidental. Space without time struggles to support change. time without space struggles to support meaning. Each lacks what the other provides. Rather than opposing concepts, they appear to be mutual supports. Remove one, and the other becomes unstable. This does not diminish time, it grounds it. Time is not a lonely river flowing through nothingness. It is a dimension woven into structure. It orders events, but those events must exist somewhere. As cosmology continues to explore the earliest moments of the universe, these questions grow sharper. What existed before familiar spacetime emerged? Whether such a before even makes sense? Whether time itself had a beginning? Those questions are approached carefully without rushing to conclusions. For now, what can be said is modest and precise. Time gains meaning through structure. It orders change, but it does not create it alone. Without space or something playing a similar role, time loses its footing. The mirror question remains open, but it reflects the same pattern. Just as space alone struggles to exist meaningfully without time, time alone may not stand without space. And in that shared dependence, the unity of spacetime quietly asserts itself once more. When the universe is followed backward with care, something unexpected happens. The familiar stage on which everything unfolds begins to shrink along with the story itself. Distances shorten, temperatures rise, structures simplify. Eventually, even space-time, the framework that holds space and time together, starts to lose its familiar meaning. This idea did not appear suddenly. It emerged slowly, built from many independent observations that quietly pointed in the same direction. Galaxies are moving away from one another. The farther they are, the faster they recede. This pattern, measured carefully over decades, suggests that space itself is expanding. Not objects moving through a fixed background, but the background itself stretching. If space is expanding now, then earlier it must have been smaller. Tracing that expansion backward leads to a universe that was denser, hotter, and more tightly packed. Matter and energy were closer together. Light was trapped in a fog of charged particles. Structures like stars and galaxies had not yet formed. This is not speculation. It is supported by several independent lines of evidence. One of the clearest is the faint background glow that fills the universe. Discovered accidentally in the mid-20th century, this radiation is remarkably uniform and arrives from all directions. It carries the signature of a universe that was once hot, dense, and nearly featureless. NASA has studied this background radiation in exquisite detail using space-based observatories. Tiny variations in its temperature reveal how early structure formed. These measurements match predictions made by models in which space-time itself was evolving from a simpler beginning. Another line of evidence comes from the abundance of light elements. The proportions of hydrogen, helium, and lithium observed today align precisely with calculations of nuclear processes that would have occurred when the universe was young and extremely hot. These calculations depend on both time and space evolving together in the early cosmos. Taken together, the evidence suggests that space-time did not always look the way it does now. As scientists push these models further back, they reach a limit, a point where densities become so high and distances so small that current physical descriptions break down. Equations stop producing sensible answers. Familiar concepts lose their footing. This limit is often described as the beginning of space-time. That phrase can sound dramatic, but it is better understood as a boundary of knowledge rather than a violent event. It marks the point beyond which existing theories no longer apply. Not because something exploded, but because the framework itself was coming into being. At this boundary, asking what happened before becomes problematic. Before implies time, where implies space. If space-time itself is emerging, then those questions may not be well defined. It is not that there is an answer being withheld. It is that the language no longer fits. This is one of the most difficult ideas to absorb because it conflicts with how thinking usually works. Causes precede effects. Moments lead to other moments. Stories have beginnings that occur in time and place. Here, the beginning is of time and place themselves. This does not mean that nothing existed. It means that whatever existed did not exist within space-time as currently understood. The universe may have been governed by deeper principles, ones not yet fully described. Physicists approach this region cautiously. Some theories suggest that space-time emerged smoothly from an earlier phase. Others propose that familiar concepts dissolve into something more abstract, where notions like distance and duration no longer apply. These ideas are actively explored, but none are yet confirmed. What is consistent across approaches is the recognition of a boundary. Up to a certain point, space-time behaves predictably. Expansion can be measured, curvature can be calculated, time orders events. Beyond that point, the tools stop working. The universe does not offer clear answers, only silence where questions lose meaning. Importantly, this boundary is not a wall in space. It is not a location that could be reached by travelling far enough. It is a limit in time itself, a limit to how far the story can be extended backward using current understanding. This is why cosmologists speak carefully. They do not describe the beginning as a moment in time, but as the earliest moment time itself can be meaningfully defined. The distinction matters. The calmness of this picture is often overlooked. There is no need for fire or shock or sudden motion. The beginning of space-time can be described as a gradual unfolding of structure, relationships becoming defined, distances acquiring meaning, durations beginning to order events. From that perspective, the early universe was not chaotic. It was simple. As space-time expanded and cooled, complexity emerged naturally. Particles formed, forces differentiated, matter clumped, stars ignited, galaxies assembled. Time did not drive this process. It ordered it. Space did not contain it. It enabled it. Even now, space-time continues to evolve. Expansion has not stopped. The universe is still changing its scale, still shaping the context in which events occur. The beginning was not a finished act. It was the start of an ongoing structure. This view also reframes what beginnings mean more generally. In everyday experience, a beginning happens within an existing setting. A door opens, a clock starts, a journey begins from somewhere. The beginning of space-time does not fit this pattern. It is not an event within the universe. It is the emergence of the framework that allows events to exist at all. That subtle difference matters. It suggests that the universe did not begin in space and time. Space and time began with the universe. This idea is not presented as a final answer. It is a conclusion drawn carefully from evidence, open to revision as understanding deepens. Physics remains humble at these limits. But even with that humility, the implication is clear. There was a stage where there was no stage, a period where distance and duration had no meaning, a boundary beyond which the words before and after no longer apply. Once that idea settles, quietly and without drama, it leaves a simple realization behind. Space-time, for all its vastness and familiarity, has a history, and before that history began there was no space, there was no time, there was only the silence where structure itself had yet to appear. As space-time settled into its role as the quiet structure beneath gravity and motion, physics appeared, for a time, remarkably complete. Relativity described the large-scale universe with precision. Geometry explained gravity. Observation confirmed prediction again and again. Then physics looked closer. At the smallest scales ever measured, nature behaved very differently. Particles did not follow smooth paths. Outcomes became probabilistic. Events resisted precise prediction. The tidy geometry of spacetime began to look less certain when examined up close. This was not a failure of measurement, it was the domain of quantum physics. Quantum theory excels where relativity does not. It describes atoms, particles, and interactions with extraordinary accuracy. It powers modern electronics, lasers, medical imaging, and the devices that quietly fill everyday life. Its predictions are among the most precise ever tested. And yet, when quantum physics and relativity are placed side by side, tension appears. Relativity treats spacetime as smooth and continuous. Geometry bends gently under mass and energy. Motion follows well-defined paths. Everything fits together cleanly. Quantum physics, by contrast, thrives on discreteness and uncertainty. Quantities come in smallest possible units. Outcomes are described by probabilities rather than certainties. Smoothness gives way to granularity. When physicists try to apply both descriptions at once, cracks appear. At the smallest scales imaginable, spacetime itself begins to misbehave. Calculations predict wild fluctuations. Geometry loses stability. The idea of a smooth structure breaks down. The equations stop cooperating. This does not mean either theory is wrong. Each works extremely well within its own domain. The problem arises only when both are required at the same time, such as near the earliest moments of the universe or deep inside black holes. In those extreme conditions, spacetime may not behave as a smooth background at all. This possibility has led physicists to a quiet but profound suspicion. Spacetime itself may not be fundamental. Just as temperature emerges from the collective motion of particles, spacetime may emerge from deeper ingredients. Ingredients that do not look like space or time individually, but give rise to them when viewed at larger scales. This idea is not new, but it has gained increasing attention as experiments probe deeper into nature's foundations. Facilities like CERN explore particle interactions at energies high enough to reveal subtle patterns. While these experiments do not directly observe spacetime breaking down, they test the limits of existing descriptions. They help identify where familiar concepts begin to strain. At the same time, theoretical work has explored many possibilities. Some approaches suggest that spacetime is built from tiny discrete elements, linked together like a vast network. Others propose that spacetime emerges from relationships between quantum states, with geometry appearing only when those relationships become sufficiently organized. In some models, distance is not fundamental, it is derived. Events appear close or far apart because of how strongly they're connected, not because of any underlying spatial grid. In others, time itself emerges from change, rather than existing as a background parameter. Ordering appears only when systems interact and information flows. These ideas can sound unsettling, but they share a calming feature. They do not discard space-time, they explain it. Just as solidity emerges from atoms that are mostly empty space, the smooth space-time described by relativity may emerge from a deeper, less intuitive layer, one that becomes invisible when viewed from a human scale. Importantly, none of these ideas are confirmed yet. They are careful proposals guided by mathematics and consistency, rather than direct observation. Physics remains patient. It does not rush to declare victory. What is striking, however, is the convergence. Independent approaches developed by different groups using different assumptions keep circling the same conclusion. Spacetime behaves beautifully at large scales, but may dissolve into something else at very small ones. This mirrors earlier discoveries. Solidity once seemed fundamental until atoms were discovered. Continuity once seemed obvious until quantum theory revealed discreteness. Spacetime now occupies a similar position, indispensable, accurate, and perhaps emergent. Even the language of modern physics reflects this caution. Researchers increasingly speak of spacetime as effective, reliable where tested, approximate rather than ultimate. This does not weaken relativity, it strengthens it by placing it in context. Relativity describes how space-time behaves once it exists. Quantum approaches may describe how space-time comes to exist at all. The tension between the two is not a contradiction to be erased, but a clue. It suggests that the universe may be layered, that familiar structures arise from deeper rules, that geometry itself might be a large-scale expression of something quieter underneath. This also reframes earlier questions. If space-time had a beginning, perhaps that beginning involved a transition from a spaceless, timeless description to the one now experienced. If space-time bends and stretches, perhaps it does so because it is not fundamental but responsive. In this light, the idea that space-time might emerge from something deeper feels less radical and more natural. Physics has encountered this pattern before. Again and again, what appears basic turns out to be composed. What seems continuous turns out to be built from discrete steps. What feels absolute turns out to be contextual. Space-time may be the next chapter in that story. For now, the evidence remains indirect. Experiments continue. Theories are refined. Observations push closer to the limits where new behaviour might appear. What can be said calmly and carefully is this: space-time works. It describes reality with remarkable accuracy across enormous ranges of scale. But it may not be the final layer. Beneath the geometry that bends light and shapes gravity, there may lie something more abstract, something relational, something that gives rise to distance and duration rather than requiring them. If so, space-time would not be the foundation of reality. It would be one of its most beautiful consequences. After following space-time through motion, gravity, beginnings, and quantum questions, a quieter issue remains. What exactly is space-time? Is it a real thing in its own right, woven into the universe like matter and energy? Or is it a powerful description, a way of organizing relationships that feels solid only because it works so well? Physics does not rush to answer this. In everyday life, reality feels straightforward. Tables are real, clocks are real, distances feel tangible, time feels persistent. Space-time, by contrast, is never encountered directly. It is inferred, measured through effects, reconstructed from patterns. That difference matters. Some physicists take space-time to be fundamental. In this view, space-time exists independently, much like a landscape. Objects move within it. Fields spread across it. Curvature shapes motion. Matter and energy interact with it, but do not create it from nothing. Space-time is part of the universe's basic inventory. This perspective fits comfortably with general relativity. The equations treat space-time as something that can bend, stretch, and respond. Geometry plays an active role. Gravity is not added on, it is built in. For many purposes, this view works beautifully. Observations support it. Light bends where space-time curves. Clocks tick differently where geometry changes. Predictions match measurements across enormous ranges of scale. From this angle, space-time looks as real as anything else physics deals with. Other physicists take a more cautious stance. They note that many things once thought fundamental turned out to be descriptive. Temperature feels basic, yet it emerges from the motion of particles. Pressure feels real, yet it is a collective effect. Even solidity dissolves under closer inspection. From this perspective, space-time might be similar. It may not be an ingredient of reality, but a large-scale pattern that arises when deeper rules interact in certain ways. Geometry could be a summary, not a cause. Space-time might be how relationships appear when viewed from far enough away. This view gains traction when quantum physics enters the picture. At very small scales, space-time behaves awkwardly. Calculations suggest instability. Smooth geometry becomes difficult to maintain. Some descriptions stop making sense altogether. These hints suggest that spacetime may be an approximation, accurate but not ultimate. In this interpretation, spacetime is real in the way a wave is real. It exists, it can be measured, it has consequences. But it is not fundamental. It emerges from something more basic. There are also hybrid views. Some approaches treat spacetime as partly real and partly descriptive. Certain features may be fundamental, while others emerge. Time might arise differently from space. Geometry might be fundamental at large scales, but dissolve at small ones. Physics allows for these nuances. It does not insist on simple answers where complexity is warranted. Importantly, these perspectives do not fight with one another in practice. Engineers using satellite systems do not need to decide whether spacetime is fundamental. They need it to work. Astronomers mapping galaxies do not pause to ask whether spacetime is emergent. They use it because it describes observations reliably. NASA does not choose sides when navigating spacecraft. It applies the framework that matches reality at the scale of interest. That pragmatism is a feature, not a flaw. This highlights an often overlooked aspect of science. Reality does not demand a single metaphysical label to function. Multiple descriptions can coexist, each useful within its domain. A map can be accurate without being the territory. A rule can be reliable without being ultimate. Spacetime may occupy a similar role. When viewed from the scale of stars, planets, and people, spacetime behaves like a real structure. It bends, stretches, and guides motion. Treating it as real leads to correct predictions. When viewed from the scale of particles and quantum interactions, spacetime may look less solid. Relationships may come first. Geometry may follow. The same concept that feels fundamental at one scale may feel derived at another. This layered view of reality has precedent. Light behaves like a wave in some experiments, and like a particle in others. Neither description is wrong. Each reveals something true under specific conditions. Spacetime may be similar, sometimes a structure, sometimes a summary. The temptation is to ask which interpretation is correct. Physics resists that temptation. Instead, it asks which description works, where, and why. It values consistency over certainty. It prefers questions that can be refined to answers that must be defended. This approach allows uncertainty to be meaningful. Uncertainty here is not ignorance. It is a recognition of limits. A boundary where current evidence does not force a single conclusion. Within that boundary, multiple ideas can coexist, guiding research without closing doors. This openness has driven progress before. Atoms were once debated, waves and particles were once argued over. In time, deeper frameworks emerged that accommodated both perspectives without erasing them. Spacetime may be awaiting a similar synthesis. Until then, it remains both indispensable and mysterious, a structure that shapes reality, and a description that may arise from something deeper, a thing that feels real, and a concept that may not be final. Holding these possibilities together does not weaken understanding, it enriches it. Rather than demanding a verdict, physics allows space-time to remain slightly unresolved. Not vague, not confused, just open. That openness is productive. It invites new questions. It supports careful exploration. It keeps curiosity engaged without forcing premature conclusions. Whether space-time is the foundation of reality or a remarkably successful description, it continues to do its quiet work, guiding motion, ordering events, shaping the universe in ways that can be measured, tested, and trusted. And perhaps that is enough for now. Space-time does not need to declare what it ultimately is. It only needs to continue making sense of what happens. And it does. After tracing space-time from everyday motion to cosmic beginnings and quantum uncertainty, it becomes natural to ask why this question still matters. Why spend so much effort wondering whether space and time are the same thing? Why revisit an idea that seems settled enough to guide satellites, predict eclipses, and explain gravity? The answer is that space-time sits quietly at the center of some of the deepest questions physics can ask. Consider black holes. In these extreme regions, space-time is stretched and curved to its limits. Paths that once led outward now turn inward. Time itself behaves strangely. From a distance, objects appear to slow as they approach the edge. From nearby, everything continues as usual until familiar rules finally fail. Black holes are not just massive objects. They are laboratories where space-time is pushed to extremes. What happens there depends critically on whether space-time is fundamental or emergent. If space-time is the deepest layer of reality, then black holes represent its most dramatic expression. If space-time emerges from something deeper, then black holes may reveal cracks where that emergence breaks down. This question shapes how physicists think about what happens inside them, how information behaves, and whether anything meaningful can be said about their interiors at all. Cosmology faces a similar dependence. The history of the universe is written in space-time. Expansion, structure formation, and cosmic evolution all rely on how space and time behave together. Models of the early universe depend on whether space-time itself came into being smoothly, abruptly, or as a consequence of deeper rules. If space-time is fundamental, then its beginning marks a true boundary. If space-time emerges, then what appears to be the beginning may be more like a transition, where one description gives way to another. These distinctions are not philosophical decorations. They affect how models are built, what predictions are made, and which observations are sought. NASA designs missions based on assumptions about spacetime's reliability across enormous distances and timescales. Telescopes interpret ancient light using spacetime as their organizing framework. At the larger scale, spacetime determines how the universe expands. At the smallest, it determines whether known laws can be extended or must be replaced. Between those extremes lies everyday life. This is where the question quietly reconnects with experience. Every memory, every plan, every expectation rests on an assumption about time. Every movement, every location, every journey rests on an assumption about space. These assumptions feel so stable that they are rarely examined. Yet modern physics shows that they are not absolute. Time can stretch. Space can bend. Order can depend on perspective. What feels universal turns out to be contextual. This does not make reality fragile. It makes it richer. Understanding space-time reshapes how familiar experiences are interpreted. Aging becomes a path rather than a countdown. Movement becomes a negotiation between space and time rather than a simple change of position. Stillness becomes relative, not absolute. Even the idea of now becomes local. Each observer carries their own present, defined by motion and circumstance. This does not isolate individuals. It situates them precisely within the universe's structure. The question also matters because it guards against complacency. History shows that concepts once thought fundamental often turn out to be approximations. Air seemed continuous until molecules were discovered. Heat seemed basic until energy and motion explained it. Space-time now occupies a similar position. Powerful, accurate, possibly incomplete. By continuing to ask whether space-time is fundamental, physics keeps itself open to deeper understanding. This openness has practical consequences. New technologies often arise from questioning basic assumptions. Quantum mechanics once seemed abstract. Today it underpins entire industries. Relativity once felt counterintuitive. Today it guides navigation and communication. Future insights about space-time may reshape technology in ways not yet imagined, or they may simply deepen understanding, which has value of its own. There's also a quieter reason the question matters. Space-time shapes how reality is narrated. It determines how stories are told, how causes lead to effects, how beginnings and endings are framed. If space-time itself is not fundamental, then narratives about the universe may need to be told differently. The beginning of everything may not be a moment. The end may not be a place. Progress may not be a movement forward so much as a reorganization of relationships. These ideas do not erase meaning. They expand it. Importantly, none of this requires abandoning everyday intuition. Daily life works perfectly well within its own approximations. Clocks remain useful, distances remain navigable, cause and effect remain reliable. Physics does not ask for discomfort, it offers context. Space-time may be the language reality uses to speak at certain scales. At others, it may fall silent, giving way to a deeper grammar. Understanding where that transition occurs is one of the central tasks of modern science. And that brings the question full circle. Is space and time the same thing? After exploring motion, gravity, beginnings, and quantum hints, the question no longer sounds like a puzzle about labels. It becomes a question about structure, about whether separation is fundamental or convenient, about whether the universe prefers division or unity at its deepest level. The answer, for now, remains gently unresolved. Space and time behave as one in every test that can currently be performed. They bend together, they stretch together, they define events together. Whether they arise together from something deeper is still unknown. Perhaps the better question is not whether space and time are the same thing. Perhaps it is why the universe insists on treating them as inseparable, and in that softened form the question continues to matter. From the beginning, the question was never loud. It did not announce itself with urgency or demand a verdict. It simply lingered, quietly, beneath familiar experiences, distance, duration, motion, waiting, aging, arriving, leaving. Space and time feel obvious because they never leave. Yet as the universe has been examined more carefully, that familiarity has softened. Space stretches, time slows, motion reshapes both. Gravity bends them together. Beginnings blur, certainty loosens. What once seemed like two separate ingredients begin to behave like one structure, or perhaps like two views of something deeper still. So the question returns, unchanged in wording but altered in meaning. Is space and time the same thing? Physics does not answer by pointing to an object or a substance. It answers with relationships, with events, with patterns that hold across motion and scale. Space and time appear less like containers and more like ways of describing how things are connected. Distance becomes a measure of separation between events. Duration becomes a measure of ordering. Neither stands alone. Each gains meaning through the other. From this perspective, space and time may not be things at all in the usual sense. They may be aspects of how reality arranges itself, ways the universe keeps track of change without needing a central clock or a fixed stage. This does not make them less real. Waves are real without being solid. Temperature is real without being tangible. Music is real without existing as an object. Space-time may belong to that same category. Something that emerges from relationships yet governs them in return. Whether space-time is fundamental or emergent remains open. Whether it dissolves into something deeper at smaller scales is still unknown. What is clear is that it works, quietly, reliably, everywhere it has been tested. Perhaps that is enough for now. Not every question needs to close. Some widen understanding simply by being held carefully. Space-time invites that kind of attention. It rewards patience rather than certainty. Space and time still feel separate in daily life. That feeling is useful. It keeps the world navigable. But beneath it lies a structure that is calmer, more unified, and more subtle than intuition suggests. Nothing needs to collapse into mystery here. There is no loss of clarity, only an expansion of perspective. The universe continues, events unfolding, paths traced, light travelling patiently across vast distances. Space and time continue to guide that unfolding, whether as a single fabric or as the surface expression of something stranger still. And in that quiet uncertainty, there is room to rest. Not knowing, it turns out, can be spacious. And time, whether flowing or simply ordering change, allows the question to remain gently open, exactly where it belongs.